morning, and welcome to this deep dive into the foundational language of mathematical logic. Mathematics, at its heart, is more than just calculations. It is a structured language for reasoning. To speak and understand this language, we first need to master its essential vocabulary, the symbols that represent complex ideas in compact, precise terms. Today, we'll build your mathematical vocabulary, breaking down symbols into intuitive groups, from set operations to basic constraints. Let's get started. First, let's explore quantifiers. Think of them as mathematical quantifiers. The backward E represents there exists. It asserts that at least one object meets a certain condition. The crossed out backward E is its direct negation. There does not exist, meaning no objects meet the condition. Finally, the upside down for all stands for every, for all. This is a universal statement, meaning the condition holds true for absolutely every element in a given domain. These form the very basics of mathematical proofs. Next, we use logical connectives to combine simple mathematical statements into more complex arguments, just like grammar connectives in English. Second, let's explore logical connectives. The tilde is not. It flips a statement's truth value. The upward-pointing wedge is and, requiring both statements to be true. The downward-pointing wedge is or, which is typically inclusive, meaning one or both statements must be true. For implications, we use the right-facing arrow gives to represent implies, stating that if the first statement is true, the second must follow. And for statements that are perfectly equivalent, we use the double-headed arrow for if and only if, showing a deep logical connection in both directions. Thirdly, let's look at how elements relate to sets in membership and inclusion. A key concept is represented by the stylized E belongs to, meaning belongs to or is an element of a particular set. Its opposite, the crossed out E does not belong to, means an element does not belong. This distinction between membership and non-membership is foundational to set theory and logic. Fourth, how do we combine and analyze the sets themselves? We use set operations. These function like addition or multiplication, but for collections of objects. The upward U represents the union of sets, creating a single new set that includes everything from both original sets. The downward U stands for intersection, forming a new set that includes only the elements that are shared by both original sets. This visual grouping is essential for visualizing relationships in mathematics and computer science when one entire set is contained inside another. We use the sideways U with a bar for is a subset of, or the reversed version for is a superset of. It's like checking if one box fits inside another. Lastly, to set conditions for defining elements within a set, we use simple symbols like a colon or a vertical bar, which are read directly as such that this allows us to create precise descriptions, like the set of all even integers such that x is greater than 0. Fifth, let's establish the common universes or domain number sets that mathematical entities belong to. We use specific double-struck or bold letters as shorthand. The tune with a double stroke A represents natural numbers, the set of all positive whole numbers, sometimes including 0, depending on the context. The Z with a double stroke P represents integers, which are all whole numbers, negative and positive, including 0. The double struck QA stands for rational numbers, any number that can be expressed as a simple fraction, where the numerator and denominator are integers. The bold RX represents real numbers, the set containing all rational and irrational numbers, covering every point on the continuous number line. Finally, the C with a double stroke A represents complex numbers, the most comprehensive set, which includes real numbers and those with an imaginary component. Next, we use comparison operators to form basic inequalities and statements of relationship between quantities. These are the core tools for measuring and relating numbers. The equals sign equals denotes equal to. Its crossed out version does not equal is its negation, not equal to. The angled brackets greater than and are simple. The wide mouth always points to the larger value. So greater than is greater than and is less than to add inclusive conditions. We add a bar below the angled brackets, the side weighs V. With a bottom bar is less than or equal to is less than or equal, and its reversed version is greater than or equal to is greater than or equal. These operators are essential for defining ranges and relationships in algebra, geometry, and calculus. Now we move to grouping symbols, which act as the essential structural delimiters in mathematics. Directing the logical order of operations. In complex expressions, we prioritize from the outside in. First are the curly brackets, known as braces. These are often used as the outermost layer. Inside these, we use square brackets. Known as brackets, the final, innermost layer of organization uses the curved lines, which are parentheses, while all three are often called brackets casually. Knowing their specific names and ordered hierarchy is critical to correctly evaluating any multi-step mathematical expression. They create necessary structure and clarity, ensuring a unique and logical interpretation of formulas. Continuing on, we have specific shorthand notation for describing multiplicative relationships, ratio and proportion. The simple colon is used to denote ratio. It compares the relative sizes of two or more values. A ratio statement like x to y is expressed as x, y. A double colon is used to indicate a mathematical proportion. It states that two ratios are equivalent to each other. For example, a, b, c, d reads as the ratio of a to b is the same as the ratio of c to d. This allows us to scale relationships and solve for unknowns efficiently. Lastly, we cover a few important miscellaneous symbols that serve as specialized punctuation in advanced mathematical text. An exclamation point has a special mathematical meaning, standing for factorial. For a non-negative integer n is the product of all positive integers less than or equal to n. Moving to logical structure. A small pyramid of 3 dots therefore represents therefore. It marks a key step in a proof where a conclusion is drawn from previous premises. A reversed pyramid of 3 dots because stands for since, used to introduce a reason or premise that supports a statement. Finally, the common percentage symbol % retains its standard meaning, denoting a percentage, expressing a number as a fraction of 100, and there you have it. A solid foundation in the language of mathematical logic, from number sets and comparison operators to the structural notation that binds them together. These symbols aren't barriers to understanding. They are elegant, efficient keys that unlock clarity and conciseness in formal thought. By mastering this vocabulary, you move beyond simply solving problems. You gain the tools to construct rigorous proofs and communicate complex ideas with mathematical precision. Keep practicing this universal language.